All right, welcome back. So last time we talked about heat and specific heat. So basically heat is transfer of energy from the higher temperature object to lower temperature object. We use Q as the quantity heat, and then we use the SI unit of joule for this quantity J. Um, and we talked about the equivalent of heat and energy, basically mechanical energy or gravitational potential energy in this case. That was demonstrated by James Joule. And we talk about the heat capacities or specific heat capacities. So specific heat capacity is related to the heat given to the object or taken from the object. So Q has been the heat added to the object or taken off from the object equal to the mass of the object times the specific heat capacity C times delta T, the temperature change. Specific heat capacity has a SI unit of joules over kilograms times Kelvin, or joules over kilograms times degree C, because we have delta T in the equation. So Kelvin or temperature Celsius, they are equivalent, right? So 1 degree in Kelvin for that temperature difference is the same as 1 degree in Celsius temperature difference. And we talk about the calorimeters, where this is a device you can use to measure the specific heat capacity of an unknown object. Okay, so by using a known material, you'll be able to determine the specific heat capacity of the unknown materials. So basically, Q of cold plus Q of hot will be equal to 0. Now, sometimes you may be having more than two substance brought in contact, so then you might have, say, 2Q for cold objects and plus a Q for one hot object, or maybe you have 1Q of cold plus 2Q of hot in that sense. But basically, you can do Q1 plus Q2 plus Q3, etc. They should add up to be 0. So this is conservation of basically energy in that sense. Okay, so energy transfer between the objects, that is the heat, that should be adding up to be 0 for the overall system in that case. Specific heat capacity could be dependent of the temperature. So if that's the case, then you'll be doing derivative of it. So to get the specific heat capacity, you use the differential form here. So C equal to 1 over m dq over dt. Okay. So in that sense, otherwise you can calculate it using just delta Q over delta T. So the heat added or removed divided by the temperature change in that sense, and then 1 over m also to be included. So today we are going to talk about the phase changes of the substance and the heat involved, called latent heat. So we all know that commonly you have three phases for substance, right? So for water, you will have solid form being ice, liquid form being normal water, and then the vapor. So that's the normal forms we have. And as I mentioned a couple lectures back, that water actually has more than 8 phases. So that's another topic that we can talk about for a certain amount of time, but not in this class. So in this class, we'll just be dealing with the three normal phases: solid and liquid and vapor water. Okay. So when you have, say, a liquid confined in a container, so to start with, you pour liquid in here, and then you make it isolated, so there's nothing else there. But the liquid now is starting to vaporize, so that means some of the liquid here will become vapor. So there's molecules becoming from liquid to vapor, and at the same time, actually, the other process happens. So some of the vapor molecules, they will come together, become liquid. So that's a condensation process. So vaporization and condensation, they happen at the same time. And a certain moment later, so initially vaporization happens faster than condensation. So that means more liquid will be vaporized than vapor being condensed in essence. But at a point, you'll reach that vaporization and condensation speed are the same in equilibrium. So that means the same amount of the liquid becomes vapor at the same time, the same amount of the vapor becomes liquid. Okay, so then equilibrium is reached. So you can measure the pressure inside here for the um, gas here, and which is called equilibrium vapor pressure certain liquid. Okay, and it depends on temperature. If you have a higher temperature, then the pressure equilibrium vapor pressure actually will be higher as well. Okay, so equilibrium vapor pressure is proportional to time. Now, if you plot that equilibrium pressure versus time, you get this curve, which is called vapor pressure curve. Now, this curve will determine when is your liquid is going to be boiling. So, for example, we know that at atmospheric pressure, right, water boils at 100 degrees Celsius, so that point. So, and if you are at different pressure, so for example, if you go higher in altitude, so let's say if you are in a mountain where the pressure, atmospheric pressure decreases, then the boiling temperature also decreases. In this case, looking at something about like 90 degrees. Okay, so in that sense, your boiling temperature now is less. Now the temperature of liquid will not go higher because it starts to boil at this time. And in a few moments, we are going to see that when the two phases are in coexistence, the temperature stays constant. So in this case, when it's boiling, vaporization happens at very fast speed. Now there's vapor and liquid at the same time. So equilibrium happens at that time. So temperature will not go up. So that's why if you are at the area that is higher in altitude, then you might want to cook your food more time. So for example, in Denver, the 3-minute egg rule doesn't apply. You probably want to cook your egg longer in that sense because the water boils at less than 100 degrees Celsius. Okay. The application, one of the applications here is the pressure cook. So you guys should have heard about a pressure cook, which is cooking food at higher temperature than 100 degrees Celsius, right? So that is the insulated environment where the pressure inside will be building up because it's insulated. So when more vapor is inside, that means more gas is inside. So then pressure will be actually increasing in that sense. And then why that's the case, why more molecules gives you more pressure, we'll talk about in the coming chapters. So basically more molecules, you can imagine you have more than molecules hitting on the wall on the container, which gives the container more force, right, to experience. So then pressure will actually increase. So for a pressure cook, if the pressure is at 2 atm, 2 times of atmospheric pressure, then the boiling temperature is about 120 degrees. Okay, so then you are cooking the food at much higher temperature. In chemistry, you know that if the temperature is higher, the reaction rate actually will be much faster. So this is again just related to chemistry, but I say a lot like cooking is kind of applying chemistry in your daily life. So when food is cooking, a lot of chemical reaction happens, right? So that's the case there. So when temperature is higher, then you are cooking this at much faster speed. Okay, so you will actually use less time for cooking when you have a pressure cook, which reduces the energy consumed, right, in a sense. All right. Now, the plot of pressure versus temperature is called phase diagram. So in which if you look at the phase diagram, and for example, this is a phase diagram for water. So then you can see if you are in this region over here, then you realize then the H2O in this case will be in a solid state. Okay? If your condition is over here at certain temperature and pressure, then you'll find it's in liquid status. Over here, you get vapor for H2O. Now, there's some cases the three could coexist as in this case. So this is called triple point. Okay? In this case, solid, liquid, and vapor H2O could coexist at the same time. But then if that's the case, then you immediately know what will be the pressure and temperature. Okay, so the pressure will be about 0.006 of atm, and then temperature will be about 0.01 of degrees Celsius. Okay, or if you are given a condition that, let's say, if pressure right now is 1 atm, right, somewhere here, and you are at, say, 50 degrees, so then you realize, okay, then this is going to be the liquid. Okay, H2O is in liquid form. And if you are given, say, again, 1 atm, and then it says 120 degrees, so you are over here, right? So then you realize, okay, then this is vapor. Okay, H2O being vapor status. So a phase diagram tells you under a certain condition what would be that substance in the phase of it will be. Now, if you have a substance have a starting point, right? So let's say under 1 atm, you are starting from minus 20 degrees Celsius here, right? So you realize it's in a solid state, right? Now, if you have heat added, so if you add heat, so then the solid ice, the temperature will increase, right? So now it might be somewhere, say, minus 15 degrees Celsius, and then keep adding heat into the ice, and now it might be minus 15, whatever, and then keep increasing until you reach zero, right? Because we know at ambient pressure, 0 degree, then that's the time, that's the moment when ice is going to starting to melt, right? So when it's melting, the temperature of it actually stays constant. So when you have two phases exist, the temperature remains the same. Okay, so even you are adding heat to that. So during this process, your heat is increasing in the horizontal direction. That's the heat. And your temperature, vertical exit. So the temperature stays constant at zero. And until you have all the ice being melted, now you have just water at this point. Okay, so in between this is ice and water, and the starting point over here, you just have pure ice. Okay, so then after that point, when water is fully melted, if you keep adding water or adding heat to the water, now the temperature of water is going to be raising up. Okay, until now your temperature of water reaches 100 degrees Celsius, where now the water start to vaporize. Okay, so in that sense, then after that point, adding heat to it will not increase the temperature again, but the water now is going to be becoming vapor in a sense. Until it's fully vaporized, then now you have collection of H2O in the form of steam or vapor. Now you heat the system again, the temperature will just go up. Okay, so that's what happens. Okay, when you add heat to the solid form of ice. And some other similar substance as well, maybe like, say, oil or dry ice or whatever in that process. Okay, so the key here is when the phase transitioning is happening, the temperature of the system stays constant. So as you're adding heat while it's undergoing phase transition, the amount of heat needed to fully melt it, the substance is called latent heat. Okay, so from ice, solid to liquid, okay, water here, and also there's a latent heat from liquid to vapor. Okay, so latent heat, we use symbol L, and so when you're adding heat, the solid will melt, right? Now um, on the other process, if you are removing heat from, let's say, water, right, then the water will become ice. So in that sense, so the forward process and reverse process, the heat added or removed, they are the same. Okay, the same amount of the heat is either added to or removed from. So Q equals to then mass times L. Okay, in this case, because the temperature is not changing, so you don't have a temperature changing term here, but just the mass of substance times the latent heat. Okay, when you are having the melting process, or the other way around, the freezing process. Okay, so this is called latent heat of fusion. Okay, so latent heat of fusion, F sub L. When you are having the vaporization or condensation process, this is called the latent heat of vaporization. Okay, so L sub F. Okay, or L sub V. L sub F for latent heat of fusion, L sub F for latent heat of vaporization. Okay. You could also have phase transition directly from solid to vapor. So for example, dry ice, it can undergo from solid form to vapor directly. So if that happens, or the other way around, you can have vapor becomes the solid directly. So this happens in the like early morning when the moisture vapor in the air become ice, then deposit on your glass window, your car's window, so then you get that a layer of frost on your glass, or maybe on the ground, on the grass, in that sense. Okay, so this latent heat directly from solid to vapor is called the latent heat of sublimation. So L sub S. Okay, so from solid to vapor sublimation. Okay, so you could have from solid to liquid, liquid to vapor, and from vapor to solid directly, or from solid to vapor directly, and then also from liquid to solid, from vapor to liquid. All right, so let's take a look on how you can actually solve a problem by having the latent heat involved. Okay, so I'm going to switch my camera. Okay, so this problem says you have 1.1 kilogram. I'm going to stop sharing so you can see this might work clearly. Okay, so you have 1.1 kilogram block of ice. Okay, so the mass of the H2O, okay, is 1.1 kilogram. Okay, so this is initially the ice. So I'm going to say this is ice. And its initial temperature, okay, T initial is -5 degrees Celsius. Okay, it says now you add 5.2 times 10 to the fifth joules of heat into the ice. So what's the final temperature of this system? Okay, so the ice might be melting, and it could or could not eventually vaporizing. So you'll take a look on this one. It tells you the specific heat capacity for water. So C of W is actually 4186, okay, joules over kilograms degrees Celsius. And specific heat capacity for ice, C of ice, is equal to 2090 joules over kilogram degrees Celsius. Okay, what's the final temperature? That's what you are looking for. Okay, so we are going to borrow the graph we had earlier. So starting from here, so vertical axis is the temperature in degrees Celsius, and this is Q added, the heat added, okay, in joules. I'm going to say in joules. So if this is 0 degree, then we are starting from -5. So you could pick anywhere to be your starting point. You make me say this is -5 or that is -5. Doesn't really matter. Okay. So they're going to say let's say this is -5 degrees. All right. Now you can imagine you add, so the heat added. Okay, so I'm going to write it down. Heat added, total heat added, Q total. Or I'm going to say Q added 5.2 times 10 to the fifth joule. Okay, that's how much amount added, total amount, or you can say Q subtotal. So you can see now you have ice, right? Because you add heat, so the temperature of ice will rise. Okay, So if you just add a little bit of heat, right, then it might just stop here. So maybe final temperature might be -2. So it's still in a solid form of ice. Okay. Now in this case, this looks like quite some amount of heat because it's 52 or 520,000 joules. Okay, comparing to the temperature increase of this guy. So this is 1 kilogram. It increasing one temperature by 1 degree. It's going to use just 2,000, right? This is 520,000. Okay, so looks like we should have enough that heat added to fully melt the ice. Okay, so we are going to call this, for this process, you will require Q1 of heat, right? And then there's another thing I forgot to write down here is the latent heat of ice melt. So L, this is called fusion, right? Fusion process. LF is 335. It says kilojoules, kJ, so times 10 to the third joules over kilogram. Okay. So this now ice reaches 0 degrees Celsius. So let's call this guy to be 0 degrees Celsius, 0 degrees Celsius. Okay, so it will start to melt. Okay, it looks like it's going to be melting, right? So and it might be fully melted or might be not. So we are not sure about it. So let's just assuming now you actually fully melted, right? So the amount of heat required will be Q2. So we can calculate Q1 and we can calculate Q2. We can add these two up, right? And then comparing to the total Q added. So if you now still have more, you have some heat remaining. So Q2 plus Q1 less than Q, then it's gonna to keep increasing in the form of liquid, right? So the liquid H2O water temperature is going to be increasing then. But let's just pause for right now, calculating Q1 and Q2 first, okay? So for Q1, it's going to be equal to, because this is the solid, right? Its temperature increases, right? From -5 to 0 degrees. So we are going to calculate using M, right? M of ice, right? And then C of also ice, right? And delta T. Let's call this T1 because there's multiple process there, right? So remember to use the correct specific heat capacity. In this case, you are still having ice. So then use the ice's heat capacity, not the water's, okay? So we're going to plug in the numbers, 1.1 kilogram, and then 2090 joules over kilogram degrees Celsius, delta T, right? From 0, right? Minus, right? -5 degrees Celsius, right? Okay, because this is the final for this process, right? And then initial is -5. So you get 11495 joules of energy, which is about 1.15 times 10 to the fifth joules. Okay, this is much less than 5.2, right? Or this is less. This is less, still less than 5.2 times 10 to the fifth joules. Okay. Or actually, this is not 10 to the fifth, but 10 to the fourth. 1.15 10 to the fourth. Okay. So then we'll have ice melted. At least start to melt. But let's calculate what's Q2. Okay. So Q2 equals, now you still have ice melting, right? But this is the phase transition, right? The temperature will not increase, but you should do L of fusion. Okay, so that's the latent heat required for the fully melting process. So this is 1.1 kilogram times now 335 times 10 to the third joules over kg. Okay, so this gives you 3.69 10 to the fifth joules. Okay, so you have Q1, this is your Q1, this is your Q2. So you can add these two up and see if how much is that? Q1 plus Q2, right? So this will be 1.15 10 to the fourth plus 3.69 10 to the fifth joules. That will give you only 3.81. 3.81 times 10 to the fifth joules. Still less than the 5.2 times 10 to the fifth added, total added, okay? So that means, okay, so now my ice fully melted. Now I only have liquid water, right? Now liquid water's temperature is going to be increasing, okay? It looks like now we use about 70% of the heat, right? So this is about 70% of that, or a little bit over 70%. So we are not having too much left, right? So it's likely we are going to just end it somewhere here because this doesn't look like it's going to reach 100 degrees. Okay, so we are just assuming this is final temperature is somewhere here. Okay, so this will be our final temperature somewhere here. This is the T final. And T final, according to this assumption, will be greater than 0, right? But less than 100 degrees Celsius, right? So that's going to see, we are going to see what will be the final temperature, right? So now the Q3 added, right? The remaining will be the Q3. Q3 is going to be just Q total minus Q1 plus Q2, okay? So this will be, the Q total is 5.2, 10 to the fifth joules minus 3.81 times 10 to the 5, okay? So this will be 1.39, 10 to the fifth joules, okay? Now this Q3, you can also calculate in a different way, right? You can calculate Q3 in this case. Now as the heat added, right, to the fully melted ice at 0 degrees. So that will be the mass of either ice or water. Now they are the same, okay? Times C, now in this case, you should be using water, okay? So C of water and delta T. So this is going to be 1.1 times 1.1 kilo, just kilogram, okay? Times 4186 joules over kilogram over degrees Celsius, right? Times delta F will be TF minus 0, okay? And this should be equal to this guy, right? So these two should be equal to each other. So you're setting this up to be equal to that one. Now this is 0, right? 0 goes to 0. Okay, so then you're solving for your TF. So basically, you probably can see from here now, TF is going to be just 1.39 times 10 to the fifth joules, right? Divided by here, 1.1 kilogram and 4186 joules over kilogram times degrees Celsius at the bottom, okay? So this gives you 30.2 degrees Celsius, okay? And this is should be your final answer because it's indeed less than 100 degrees, okay? If you get a number here greater than 100 degrees, then that means the water reaches 100 degrees, right? In that case, you might have to reconsider what happened here. So what happens here is it will then reach to 100 degrees somewhere here. Let's say that's 100 degrees, and then it will start to vaporize, okay? So now you have Q1, Q2, Q3, you also would have Q4, okay? So in that sense, you recalculate what will be your Q3 and then add Q1, Q2, Q3 up. Those three add up should be less than your Q total, right? And then Q total minus those three, you can calculate for this guy, so Q4. Or you can calculate Q4 first, and then add Q1, Q2, Q3, Q4 up. If those four add up to be greater than the Q total, that means you are in the partially vaporized point somewhere. So then your final temperature will be at 100 degrees because the phase transition from liquid to vapor happens at 100 degrees, right? If your Q1, Q2, Q3 plus Q4 is less than your Q total, then you'll consider the vaporization. After the vaporization process, the vapor's temperature will increase at that point, beyond that point, okay? So then you can calculate what will be the final temperature from there by similarly just doing Q total minus those four Qs, right? And then you can also calculate in the Q5, which will be now the mass of the whatever total C of the steam. So that C for the steam now at that time should be given delta T, right? Equal to the excess, any excess heat remain, okay? All right, so this will be then this guy. All right, so you have heat added to a substance, in this case, ice, and then this is how you're figuring out what will be the final temperature, okay? Now, let's get back to the slides. Now, a lot of times, you have, say, a drink, right? This is what we do normally, right? We have a drink, room temperature, right? Then we added ice, right? We want the temperature of drink to go down. So you have like a liquid water, so drink is pretty much water, and you have ice. So you have a hot object of drink and a cold object of ice, the two being brought into together. So what will be the final temperature in that sense then? So now you have more than one substance to remain, okay? So let's take a look on that. And during the process, you might also have phase transition, right? So maybe ice will be fully melted, right? Or maybe in the extreme case, you have too much ice, then the whole drink will be frozen. Okay, so in that sense, let's take a look at one problem similar to this scenario. So this one says a large punch bowl holds 3.99 kilogram of lemonade, which is essentially water, and the temperature is at 20.5 degrees Celsius. Now you add an ice cube, 0.0550 kilogram, initially at minus 10.2 degrees Celsius into the lemonade. What would be the final temperature of the system? And if there's any ice remaining, okay? So it says ignore any heat exchange with the bowl and the surrounding. So that means we are going to assume there's no heat exchange to the surrounding. It tells you specific heat capacity for water is 4186 again, joules over kilogram and times degrees Celsius. And for ice is 2090 again. The latent heat for ice melt is 335 kilogram joules. Okay, so the same numbers. So let's take a look at this guy. Okay. Let me just exit the full screen mode, sharing mode, so you can see my work on the paper better. Okay, so let's say now there's mass of water, right? I'm going to say M of W, M sub W, 3.99 kg, M of ice, 0.0550 kilogram. Temperature of water initially 20.5, temperature of ice initially minus 10.2 degrees Celsius. Okay, so it looks like in this case the ice amount is much smaller than the water, right? So we probably could expect that the ice will fully melt it, okay, and then brings the temperature of water down a little bit, okay, in that case. C of water 4186, C of ice 2090, and latent heat of fusion 335 again, kilo, so times 10 to the third joules over kilogram. Okay, so those are the norms. Let's have a similar plot here. So this would be the temperature, okay, and then this is going to be the heat exchange. All right, so let's say this is a starting point for water, so 20.5 degrees Celsius. Okay, and as I mentioned, the ice, right, starting at minus 10 somewhere here, minus 10.2 degrees. So it looks like it's going to be likely the ice temperature is going to be increasing and start to melt, right? And then the fully melted ice, its temperature is going to be increasing, right? At the same time, for the water, the temperature of the lemonade is going to be just decreasing, okay? And at a certain point, these two will meet. So then this will be your final temperature. This is your final temperature that you're looking for, okay? So then we will look at the heat for the ice, heat taken out from the ice, right? Q sub ice. In that case, and then the heat by this three process, Q1, Q2, and Q3. I'm going to call it that way, Q1, Q2, and Q3, okay? So in this case, we will just say Q1 plus Q2 plus Q3, right? Plus Q2 plus Q3. So this is the Q for the cold, right? So this is similar to the calorimeter problem. So this together will be Q of the cold, right? Plus Q, this will be Q of the hot, okay? It's going to be equal to 0. So basically, this is what we are going to apply because that's only heat exchange between the ice and the lemonade, okay? So Q1, Q2, and Q3, you can calculate them separately, right? So Q1, let's do that. So Q1 is equal to, or maybe I can use the red for the Q. Q1, for Q of the ice, Q1 is actually mass of the ice, C of the ice, right? Raises temperature all the way up to 0, and delta T1. So this is going to be 0.0550 kilogram ice, 2090 joules over kilogram degrees Celsius times delta T1 final being 0, initial being minus. So 0 minus of 10.2 degrees Celsius, okay? So this will give you 1172.5 joules, right? Now, the melting process will be M of ice times LF 0.550, 0.0550 kg, and 335 10 to the third joules over kg, okay? So this will give you 18,370 joules, okay? For the Q3, I'm going to write it over here. Q3 is equal to mass of the still ice already, although it's melted, right? It's melted, become ice, become water, but we should still just use the mass of the ice because when ice melt into water, the mass is still the same. In this case, now C, however, this will be the water because now it becomes water, and then delta T, in this case, 3, okay? So this can be written as 0.0550 kilogram, 4186 joules, okay? Kg degrees Celsius times TF, right? Minus initial will be 0, okay? So that's Q3. We do not know TF yet, so we'll just leave it there. For Q of water, QW, it's going to be just one simple equation of QW instead of Q3. QW is equal to C of W, or mass of W, sorry. Mass of W times C of W times delta T for the water, okay? So this is going to be 3.99 kilogram, 4186 joules over kg degrees Celsius, and TF minus initial 20.5 degrees Celsius, okay? So then Q1, Q2, Q3, and this is QW. they should add up to be 0. So we are going to add those two up and then set them equal to 0 according to the condition there. Okay, so you're going to say 1172.5 joules plus 18,370 joules plus 0.0550 kilogram times 4186 joules over kilogram degrees Celsius times TF, right? That 0 will not count, okay? And plus 3.99 kg 4186 joules over kg degrees Celsius times TF minus 20.5 degrees Celsius. All add up to be 0, okay? So now in this equation here, TF is the only unknown, but there are two terms with TF, right? You want to put them together, single out TF, and then move the rest stuff to the other side of the equation, okay? And solve for TF, okay? So that's purely algebra. I think you guys will just do it very well on that. So I'm going to just tell you what will be the final temperature here then. So it turns out the final temperature here by solving for this one is going to be 19.1 degrees. Okay, so it brings the temperature down a little bit. Okay, so the assumption we had initially is the lemonade temperature is going to be going down, but probably not freezing, right? So it should be just greater than 0 degrees. Okay, but still less than the initial 20.5 degrees. Okay, so that looks good. Okay, all right. Now going back to the lecture slide. So we'll move to the last section here in this chapter, talk about mechanisms of heat transfers. Okay, so heat transfers through different methods. Okay, so in this figure, you'll see that. So this is a fireplace. Okay, so depends on how heat is transferred. So it could be directly radiated. Okay, so just radiate out. It could be carried through the room air here. So this is called convection, or it could be carried through the solid floor here on the wall. This is called conduction. So it depends on how heat is being transferred. There are three different ways or methods called conduction, convection, and radiation. So conduction is through a solid material. Convection is through air. Okay, and then radiation is just a radio the electromagnetic wave. Okay, should put that in that way. Okay, so we'll look at those three methods one by one. So first, the conduction. Conduction is the flow of heat direct through a physical solid material. Okay, so let's say you have a either higher temperature here or lower temperature there. Okay, so this could be TH, this could be TC. So through this solid physical material, so then the power, the rate the heat is transferred dT over the temperature difference. Okay, it's going to be depending on the temperature gradient, TH minus TC, and the length of this guy and the cross-sectional area of that. Okay, so A is the cross-sectional area. Okay, and then D will be the length of the rod. Okay, in that case, kappa is the conductivity of the material. So it depends on what material is this guy. Okay, and then the temperature gradients. So for kappa depends on material, or K depends on material. In the same in the equation, the silver, copper, gold, those are the metals. They usually have higher conductivity, higher K, so they can conduct heat much faster. Okay, so metals are generally being good conductor. On the other hand, when you go to the other materials, like for example, ice or water and the other stuff, wood, they are actually pretty low in conductivity. So that means they are not good conductor, heat conductors. Okay, although air it's much smaller number, okay, or wool in that sense. So in the winter, your jacket may be made of wool. That's because it's a poor heat conducting material, so it keeps all the heat within the clothes. Okay, air conduct heat also very slowly, or styrofoam that conduct heat actually very slowly either. Okay, as well. So air or styrofoam could be good insulators. Okay. Down feather is also a good insulators, okay, close to air. So maybe you can just have air instead of down feathers, right? In between the layers. Okay. So make sure that is isolated air. Okay. So if it's not isolated air, then you will still conduct heat um, very quickly by convection in that sense. Okay. All right. And now let's look at convection. That's defined as the flow of fluid due to a difference in the temperature and which carries heat. Okay, so in this case, in the daytime when the shore is hotter, the ocean or the water is cold, so then the heat is being can be um, conducts through the convection of the air flow in that sense. And in the nighttime, it goes in the other way because temperature of all the water now is warmer compared to the shore. And then also in the house that you'll have some heat being conducted with through the convection as well. The last one will be the radiation. So then is the heat conduction through the radiation of the material. So when the material has temperature and it will radiate heat, okay, so then heat will go off, okay. So in this case, it can even go through vacuum. It doesn't necessarily need a medium like the convection or conduction process, okay. All right. So radiation of the heat Q over time T, the rate of radiation depends on a few factors. Okay, so the surface area of the object A and the temperature of the object, surface temperature again. So to the fourth power, E is the emissivity, okay, of an object. A perfect object will have emissivity of 1, okay, and it's anything between 0 and 1. So you might have something like 0.5, 0.2. Sigma is the Stefan Boltzmann constant number. That's a constant number, 5.67 times 10 to the minus 8. Actually, you could remember this easily because it's 5.678, right? 5.67 times 10 to the minus 8, okay, in a sense. All right. So normally you will have the object placed into an environment, right? So let's say hot object in the room. So then the room temperature will be the environmental temperature, okay? So because the room and also radiates, so then the object will also receive radiation from the room. So it gives out radiation at the same time, it receives the radiation from the surrounding as well. So then the overall process, the Q net for the object is divided by time t, so that's the rate of the heat transfer to the object. Total will be like sigma EA, and then T, this is the object's temperature to the power 4 minus T1, the surrounding temperatures to the fourth power. Okay, so this is the overall heat change of the object, okay, when it's placed into an environment. Okay, so let's take a look the radiation of our human body. Okay, so this one asks you to calculate the net rate of heat loss in radiate energy for a naked person in a room at 20 degrees Celsius. Okay, assuming the person to be a black body with a surface area of 1.4 meters square and a surface temperature of 33 degrees Celsius. The emissivity of skin is 1.00, so it's a perfect radiator. I want to point out here, although it says a black body, that doesn't mean the skin of the person. Okay, so in physics, when we talk about the thermal radiation, any object has temperature that's not 0 will give out radiation, which is called black body radiation. So that's why it's wording as a black body here. But it's an object. In this case, is the person. Okay, doesn't necessarily have to be a black person. It could be a white person. It could be like a brown person. Okay, so whatever. So let's take a look on this one. I'm going to switch my camera. All right. So here are the norms. The temperature of the person, okay, of the object, we say that's T2, right, in the previous equation. So the equation to use, the net Q, right, over T equals sigma Stefan-Boltzmann constant times E times emissivity times the area times T2 to the fourth minus T1 to the fourth, okay? So it says E is 1, and then it says area is 1.4 meters square. It says the temperature of the person is 33 degrees Celsius, which is 306 Kelvin, okay? So 306.15 basically. But it says the surrounding T1 is 20. So 20 degrees, you can calculate. It's going to be 239 or 293.15 Kelvin, okay? So we need the temperatures in Kelvin here. Okay, so then basically you take in the numbers, you calculate for this guy, okay? So the power or the net heat is equal to Stefan-Boltzmann constant 5.67 times 10 to the minus 8, okay? And that's in the unit of watts over meter square times K to the fourth, okay? Times 1 times the surface area, 1.4, okay, times 306 Kelvin to the fourth minus 293 Kelvin to the fourth, okay? All right, so then this is the heat lost of the person because the person gives the heat to the room, the surrounding, okay? So in this case, it gives you 110 watts total, okay? And you might have heard about this. So a person gives out heat is equivalent to a 100-watt light bulb, okay? So that's about close to the number, okay? So 110 watts in that sense. All right. So let me go back to the PowerPoint slide over here. There's a video here for you guys to check yourself. So you can click on here. So this is about the heat transfer of the cooking process. Okay, so you can see there's different ways of heat conductor happening in that sense. Okay, so watch that one on your own, and then we'll stop here for today, and then I look forward to the next video. Okay, so bye for today.